Good evening. My name is Mark Barnico, and I'm the Executive Director of the University of Chicago Francis and Rose UN campus here in Hong Kong. I'd like to welcome all of you to the UN campus virtually for our first episode of 1.5 Degrees. The UChicago UN campus in Hong Kong is our premier location in Asia, representing UChicago values of free and open discourse, rigorous debate, and the exchange of ideas. For more information about the UChicago UN campus in Hong Kong and all our programs and activities, please visit our website at www.uchicago.hk. And now to this evening's program. The UN campus team began talking seriously about climate change series more than 10 months ago. We recognized the challenges the world faced with increasing global temperatures, fires, floods, droughts, and other extreme and shifting weather events. The more we discussed the topic, the larger our vision for this program became. In the meantime, climate change has not taken a pause while we've all been fighting the devastation caused by COVID-19. In fact, our current unusual living and working circumstances have allowed many of us to reflect more deeply on what more of us could do to reverse course. But some experts believe it may be too late. Many believe we're well on our way to exceeding the 1.5 degree target for a global increase in temperatures. Through our one-year focus on this program, we hope to raise the personal and social consciousness of each and every audience member to these issues and what can be done to reverse course. We plan to do that through UChicago faculty-led lectures like the one we're having tonight. In addition, we'll also work to engage more of our audience in Asia through morning coffee klatch programs, outdoor socially distanced community activities, and in-person hybrid or virtual symposia, where we drill down into specific climate change topics. We hope to discuss the history of climate change, the science of atmosphere and oceans, altered migration, food, and living patterns, as well as consumption, economic systems, and the overall cost of climate change. Finally, we hope to help you understand what individuals, communities, corporations, startups, governments, and non-for-profits can do to take action. We'd like to hear from you about your work that you're doing and that's taking place in Hong Kong and throughout Asia and the world. So please share and make suggestions and recommendations to our chat box on Zoom or send them to our email on our website. We'll share those links on a special 1.5 Degrees resource page. You can all make a difference by taking small actions in your daily lives and influencing corporate and government leaders to institute programs and policies which reflect your passion, your area of interest, and your area of concern. And I promise we'll deliver cutting-edge UChicago thinking and research across a wide spectrum of the university, including history and science, economics, government policy, business, and the humanities in each and every program. Now let me introduce you to our guest lecturer tonight. Professor David Archer has been a professor in the Department of the Geophysical Sciences at the University of Chicago since 1993. He's worked on a wide range of topics pertaining to the global carbon cycle and its relation to global climate, with a special focus on ocean sedimentary processes such as CaCO3 dissolution and methane hydrate formation, and their impact on the evolution of atmospheric CO2. Professor Archer teaches extremely popular classes at UChicago on global warming, environmental chemistry, and global geochemical cycles. Professor Archer is a prolific writer on the subject of climate change. His most recent publications include The Ultimate Cost of Carbon, Climatic Change, Model of Mercury Cycling and Isotopic Fractionation in the Ocean. His books include Global Warming, Understanding the Forecast, a textbook for non-science major undergraduates. The Warming Papers, the Scientific Foundation for Climate Change Forecast. The Global Carbon Cycle, Princeton Primers in Climate. And his free open online classes, or MOOCs as we call them, include Global Warming 1, The Science of and Modeling of Climate Change, and Global Warming 2, Create Your Own Models. You can find other interesting items on Professor Archer's website, including a model called SpongeBob and a video called The Long Thaw, all on the link provided on our website. Professor Archer, welcome. We're honored to have you this evening. The floor is yours to kick off the 1.5 Degree series and deliver your lecture.
Thank you, Mark. So what I wanted to show you tonight, this morning, is how the global warming phenomenon, the climate change from combusting fossil fuels that we're provoking, fits into the natural context of Earth's carbon cycle. And so there have been climate change events in the deep past before there were people that were much worse than global warming is probably going to be. So on the one hand, perhaps we could take some comfort from that. But on the other hand, to me anyway, thinking about Earth's past climate changes makes global warming seem actually much bigger and more frightening. So I will show you what I mean, and you can judge for yourself. The first thing that you need to know about Earth's climate history is was predicated on a question called the faint young sun paradox, which is the observation from astrophysics that stars tend to get brighter and hotter as they change their composition as they age. So if you were to take the sun and the Earth as it is today, take the sun and turn it back 4 billion years so that it would have been cooler and not change the Earth would have been frozen for most of its history. And we find evidence that this is not the case, that most of Earth history there has been liquid water. So what is an explanation for this? That explanation is in a theory that we have about how the carbon cycle works. And in the course of its operation, it provides kind of a planetary thermostat mechanism that tends to regulate the temperature of the planet, even as the sun is getting hotter. So the basics of the system are that carbon is coming out of the solid Earth and going back into the solid Earth by these pathways. It comes out by volcanic emission and at hot springs at the bottom of the ocean. And it ultimately goes back to the Earth by dissolving rocks that have calcium in them, such that the calcium can bind to a carbon and make calcium carbonate that gets buried in the bottom of the ocean. And eventually some of that calcium carbonate gets heated up and the CO2 then can go back to the Earth and completes the cycle. But the part of this that provides a thermostat is this dissolving the igneous rock step, which requires liquid water for that to work. And so the more the CO2 in the atmosphere goes up, the warmer the climate, the more water is washing over the rocks and the faster you can dissolve rocks to make this calcium carbonate. So the system functions like a sink. If you turn on the water to a sink and the water level kind of rises a little bit in the sink because the drain is a little slow maybe. And eventually the water level finds the value at which it's going down the drain as fast as coming in from the faucet. And that's how this system is working. The CO2 in the atmosphere is analogous to the water level in the sink. It finds the value at which the flux is balanced. So if the CO2 concentration is pushed up by, say, fossil fuel combustion, that means that the rate of weathering, the dissolving of the rocks, will go up, and it will not balance the degassing rate anymore. So that's pulling the CO2 back down. And so this is a stabilizing mechanism, a negative feedback. And so this mechanism will eventually clean up the fossil fuel CO2, but the bad news is that it has a very long time scale for doing this of hundreds of thousands of years. So from our point of view, we don't even see it because we're not going to be around that long. So this is a reconstruction of how the atmospheric CO2 concentration has been changing over the last 400,000 years. This is from little bubbles of ice in ice cores in Antarctica. You can measure how much CO2 is in those little bubbles, and those are ancient air samples. And we see that the well, one thing we see is that time is running backwards in this plot. Paleoclimate people have this unfortunate tendency to flip time going back and forth. You'll see both ways today. It's kind of crazy, but mostly what I wanted to show this for now is that there's no long-term trend of CO2 over hundreds of thousands of years going up or down. So that means that the fluxes coming out of the earth and going back into the earth over this time, on average, were very closely balanced. Also, the fact that you have these excursions. So here's a glacial time, here's our current interglacial time, and the CO2 is not absolutely steady, means that the thermostat must be slower than sort of 100,000 years. Otherwise, the thermostat would have not allowed the CO2 to change. Here is an analog to a global warming event that happened 55 million years ago. Time is still running in this plot from right to left. What you see in these isotopic records is the trace of some big spike of carbon that was released all of a sudden that's analogous to fossil fuel carbon. And we see the temperature spiking up in the deep ocean at the same time. And then both of them are sort of returning back to their pre-excursion levels on a time scale of hundreds of thousands of years. So this is a pretty good analog of what global warming will eventually look like. Deeper in Earth's past, what we see is fluctuations of the set point of the thermostat. As plate tectonics moves the continents around, you move some easily weatherable rocks into a rainy zone that makes it easier to weather, or you move into the high latitudes where there's less water and makes it harder to weather. It's like you're adjusting the set point of this thermostat. Most of Earth history has not had ice on the planet the way we do today. We live in kind of an unusual time in that regard. Most of Earth's climate was this sort of hothouse climate where it was much warmer than today. We also see periodic or occasional large volcanic eruptions called large igneous provinces. So these are volcanic eruptions far bigger than anything that's happening today, sort of a split in the earth thousands of kilometers long, gushing out enough lava to flood whole areas of continents in kilometers thick of rock. Just horrible events like this, and they tend to correlate with mass extinctions, of which there have been 5 main ones and then a bunch of smaller ones. So those are also, it turns out, analogs to our own climate event, because a lot of the extinctions were driven by the CO2 that came out of those eruptions. So here we now see a plot where time is running the other way, and we're looking at the glacial, interglacial cycles again as we're zooming in closer to our own time. Anatomically, modern humans evolved sometime way, maybe several million years ago. It's sort of controversial. but humans with some sort of culture where you find variation from place to place or time to time in styles of pottery or tools or something like that go back about 40,000 years. So a lot of our history was spent in this ice age time when there were much bigger changes in climate throughout this time. But then there's this last little bit here. This is the Holocene. This is about 10,000 years. And it's been a time so far of incredible climate stability compared to what happened before. And that time is pretty much when civilizations and agriculture and things like that arose. So throughout the Holocene, even though it was very quiet, there have been globally synchronized changes in climate that seem to be reflected in globally synchronous rises and falls of civilization. I'm not a human historian, but I've read some books and they all are saying the same thing, that there are these times like the medieval warm period when the Vikings were sailing around the world, and followed by the little ice age when the Vikings in Greenland all died out, and there were other times sort of going back in time, the Roman warm period or the medieval pessimum is sort of here, the European Dark Age. There's dark ages in Greece that are correlated with climate changes. So thinking of humans as an indicator of climate change, we are somewhat sensitive to relatively small changes in climate. So now what's going on is that we discovered coal and fossil fuels, and we're putting CO2 into the atmosphere. And this is kind of what that looks like in sort of a broad brush. We have the rise in CO2 during the early industrial era is documented in ice core bubbles again. And then we started making measurements of the CO2 concentration in the atmosphere starting in 1958. And those measurements are here, and they line up nicely. This is I'm going to show you a quick animation of what the CO2 in the atmosphere today looks like. So before I click go, I just want to go show you what the plot is showing. We have latitude on the x-axis here. So there's the South Pole, and CO2 samples, atmospheric samples, are collected at all these different locations, different latitudes around the globe. So in 1979, this is what it looked like. When I get the animation going, you will see the value of the CO2 at this red dot. That's Hawaii. That will be in this plot here, and you will see the CO2 rising everywhere, but you will also see a seasonal cycle as the trees and plants in the northern hemisphere are breathing CO2. They take up CO2 in the summer and release it in the winter. So here we go. It's like the biosphere is breathing, and there's more land in the northern hemisphere than in the south. That's why the breaths are deeper in the northern hemisphere. In the south, it is out of phase with the north because it's summer in the south when it's winter in the north, but there's less land in the south, so less of a cycle. So then, looking at this plot from Hawaii, you see much more clearly the seasonal cycle, the breathing, and then superimposed on that is the fossil fuel carbon. So I told you about the carbon cycle as being CO2 going between the solid Earth and the atmosphere. But focusing in a little more closely, we talk about the fast carbon cycle consisting of the atmosphere and the ocean, and then the land surface, the trees and organic carbon in soils. And when carbon is unearthed from the deep earth, when it's mined and put into the atmosphere, it then spreads out through this fast carbon cycle. Some of the carbon, about half, is remaining in the atmosphere. And then there is uptake of some carbon in the oceans and some carbon into trees and soils that is sort of being provoked by putting carbon into the fast carbon cycle there. So the amount of CO2 invading the ocean actually can be measured pretty precisely by making measurements of the chemistry of water. The chemistry of the ocean is smooth enough that you can do that. Chemistry of the land surface, in contrast, is, if you dig a hole and measure how much carbon was in the dirt that was in that hole, it's, probably different from what you would get if you did it a few meters away. It's much noisier and harder to constrain. So we have a better handle on the fast carbon cycle in the ocean than we do on land. But putting together what seems to have happened we have this plot. So we're looking at the cumulative emissions or reservoir changes of carbon over time. So the fossil fuel cumulative emission has, is here, and the atmosphere contains about half of what we have burned, and the ocean contains a substantial amount. And then the land surface, you can see it was a net source of carbon in the early industrial era. This is known as the pioneer effect, when people cutting down trees to grow crops. But with agriculture getting more efficient, there's now reforestation in the temperate latitudes, while there is deforestation continuing in the tropics. Plus, there is some sort of a mysterious carbon uptake into the land surface that we don't really know for sure quite where that's happening. It's a huge amount of carbon, greater than the mass of all the human beings on Earth every year, that's disappearing someplace. And because the land is so hard to characterize, we only know it's going into the land because it's not going in the oceans, and we can measure the oceans. So the land has ended up being kind of a net zero source of carbon in the end, when you put all this complicated stuff together. So if you, here are data and reconstructions and model simulations going back and forward in time, spanning now tens of thousands of years, so a much longer time horizon than you probably have heard people talk about for global warming. So here is this change in CO2 that we saw from the ice cores, those sawtooth patterns. That's this rise from the last ice age to today. And then here is the CO2 spike from fossil fuels. And what you see is the CO2 doesn't ever come back to where it started, even though we're talking about 10,000 years into the future. You see this sort of a spike of CO2. And then here's the temperature, which also, it doesn't have as strong of a spike because that gets kind of smoothed off in the temperature. But what you see mostly is the temperature rises to a new normal and then just stays there pretty much. I mean, this plot only goes 10,000 years into the future, but we know it would be hundreds of thousands of years. It would stay that way. So CO2 is fundamentally different from most other kinds of pollution. Aerosols, smoggy air, if we just stop burning, car engines, gasoline, the air clears out in a week or something like that. Acid rain is that way too. But CO2, it just accumulates. And so it doesn't just go away as soon as we clean things up. So those temperature changes, this was a very interesting paper fairly recently that talks about the human climate niche. So we're looking at, these are basically maps of where people live today or 500 years ago or 6,000 years ago. The maps are in space of rainfall in this dimension and the mean annual temperature here. So, humans have particular places that they like to live. It's not just a function of where there are fertile soils or where there is land or even where plants grow. You see there are plants growing at much colder temperatures than humans tend to live, but it's, driven by our crops and livestock and stuff like that. So if you take those maps and think about where people like to live, they came up with these maps of suitability for human habitation. The more suitable it is, the darker the colors here. And they're comparing the present day and the year 2070, which is, enough time for temperature to have changed, but, only the very beginning of the global warming event. And then here's the difference showing, where the green areas are sort of better and the red areas are sort of worse. These are major changes that would lead to the migrations of millions of people, and migrating millions of people is not a happy thing in human history, because the people who are, in a place where people want to migrate to tend to get defensive and put up walls and try to keep people out and fight wars and things like that. So, this is really hitting us kind of where we live, is the impression I get from it. Another impact of climate change that is maybe underrepresented in how you read about global warming is sea level change. So sea level rises for several reasons, but the main one is because of the large ice sheets in Antarctica and Greenland. If they melt, the water runs into the ocean and makes the ocean higher. And so if you just Google sea level rise from global warming, you'll probably read about a forecast for sea level change by the year 2100, which is a number that's like here. But looking into the deeper past, what we find is a much stronger relationship between sea level change and global average temperature than what this forecast for 2100 would suggest. And that is because it takes thousands of years for the ice sheets to melt. The year 2100 is just, the tip of the iceberg, so to speak, of the sea level response change. So, the forecast for 2100 is maybe 1 meter of sea level rise or something like that. But if you look at the changes in temperature that we're talking about for the future and allow the ice sheets to react fully, you're talking about tens of meters, 50 meters of sea level rise, something like that, ultimately on timescales of, thousands of years. So here are some more model results from the same source of the other plot that I showed that shows sea level in the past. So here's the last ice age, and here's the sea level rise into the Holocene, our 10,000 year time of all of our civilization and agriculture and everything. And then you see over thousands of years going into the future, sea level rise that is, up to 50 meters of sea level change. So a deglaciated Greenland and a much reduced ice sheet on Antarctica are, within our reach eventually. So doing that math, if you had 50 meters of sea level rise, it turns out that's home to about 3.5% of the land area, and it's home to something like 10% of the world's population, because there's a lot of good agricultural land in river deltas that are very close to sea level. So every time I consider, putting a gallon of gas into a car or something, I think about how that is then committing to eventual loss of our home. Every little decision that we make will have this consequence. So because the CO2 accumulates rather than just kind of going away, on some sort of a human timescale, it turns out that the way that we have to regulate it is in terms of the total amount of carbon that we have ever emitted. It turns out that the more carbon you add, the more this temperature change will rise. And it's a little bit weird, but it's actually kind of a linear relationship. So you double the amount of carbon, you double the temperature change. That's kind of by chance. It didn't have to be. It could have been sort of nonlinear in one way or another, but that's kind of the way it turned out. So you end up with this sort of straight line relationship between how much carbon we've ever burned and what temperature change we can expect. However, there is considerable uncertainty in how much temperature change you'll get from CO2. It's an issue called the climate sensitivity. There's a lot of spread in the model predictions of this climate sensitivity, and it's due to hard things to model, like clouds and ocean circulation. So there's this uncertainty in what this thing will actually look like, with different slopes, and we won't really know what the right answer was until thousands of years when everything has fully responded. So there's uncertainty that's kind of baked into the problem that we have to live with. So in talking about climate change, it has sort of reached a stage where we're talking about the peak temperature that we wish to avoid. It's sort of more like a plateau temperature than a peak, exactly as you've seen. Mark mentioned, and this whole series is named after 1.5 degrees, which is an aspirational target. It's not a safety limit. So we can't say that everything less than 1.5 degrees is safe and then it gets unsafe after, but it's just a target that might be attainable. It evolved from a previous 2 degrees C target that the European Union was pushing, but then at the Paris meeting, they decided that 1.5 degrees would be better than 2. And then since there's just so much carbon that can be burned to reach that, they call that carbon space and argue about who gets to burn it. So, countries like the US that have historically burned a lot of carbon in our lifestyles, do we get to burn the rest, or should we stop and let other people burn some carbon? It's kind of, it simplifies the regulatory picture because it's just like this pie. And if you eat the pie, you get sick. And the more pie you eat, the sicker you get. It's very simple. But when people put together the sort of models of industry and energy and human, economy and stuff like that, and try to figure out, in detail what this transition to low carbon could look like and how much carbon we will have emitted by the time we're done with that. Most of the scenarios that stick to 1.5 degrees C of temperature change require what they call negative emissions, which means cleaning the CO2 out of the atmosphere. Because it's an accumulating problem, it won't go away. We might have to actually clean it up ourselves. So here is an example of a study trying to figure out what cleaning up the atmosphere would look like and cost based on chemical engineering, techniques and technologies. So this guy, David Keith, is kind of a hero in this field. And he's coming up with costs of something like $100 per ton of CO2 is how much it would cost. So, they do this in submarines, and, the technology is very easy, but you have to unmix CO2 from the air, and that takes energy. And so there's like intrinsic cost built into it. Mostly what you hear about for negative emissions is what they call biomass burning, carbon capture and sequestration. So you grow some grass and then burn the grass in a power plant and capture the CO2 and sequester it. The trouble is that would take a lot of agricultural land, and doesn't seem like we have enough of that. So that doesn't seem like a viable idea to many of us. There's also a possibility of mining a kind of a mineral that lives in the deep earth, and it would react with CO2 sort of spontaneously. So accelerating that natural thermostat kind of a thing, that might be cheaper. But if we stick with the industrial direct air capture, it turns out that if you multiply that by how much CO2 we're putting out or have put out, it's very, very, very expensive mess that we're making. So it turns out that we are releasing enough carbon that at that rate, it would cost about 3.6% of our whole economic activity to be cleaning it up as fast as we are emitting it. So, digging a hole for ourselves very quickly. And then how deep are we in debt already? Right now, the CO2 in the atmosphere is 400 and something, 410 or something like that, with a seasonal cycle going up at a few ppm every year. The safe limit for atmospheric CO2 is thought to be about 350 parts per million. That's a level at which the energy difference at the top of the atmosphere that's causing the Earth to get warmer would go to zero. And so that would mean that there's no further warming. So the climate that we have today would be what we would have, and it wouldn't get any warmer. And so that's, much less. That's 350, we're now at 400 something. So to get back down to 350 in 30 years, I calculated would require removing about 440 billion metric tons of carbon. And you do that math, and it turns out to be about 1.6 years of global world production to clean up the mess that we have made. So, you know, that's crazy. That's a lot of money. So, you know, the takeaways that I would suggest from consideration of the past are that CO2 pollution doesn't go away by itself. It just accumulates, and it's kind of, there are not many things that we do that accumulate in that way. And it would be very, very expensive to clean up. So if the sooner that we start cleaning it up, the cheaper it will be, because it's a lot cheaper to eliminate pollution, you know, before we release it than to clean it up later. And the response of the Earth system on long enough timescales is huge. You know, 50 meters of sea level rise is crazy. So I sort of view the global warming problem as just a waste management issue. There's this poet for kids named Shel Silverstein, who wrote a poem called about a little girl named Sarah Sylvia Cynthia Stout, who would not take the garbage out, and the garbage just piled up higher and higher in her house. And that's who we are. Our garbage is piling up in our house, and we have to learn to start taking it out. So with that, I guess that's what I wanted to show you. We have lots of time for questions and conversation, so I hope we can do that. Thank you very much.
Thank you, Professor Archer. That's a really interesting talk. We had so many comments on how interesting your presentation was, and many, many questions for you. So I'm going to start with a question just based on our own conversation with one another. You decided and that this was a good format for you to actually deliver the lecture virtually, as opposed to coming to Hong Kong in person. And have made a decision that you're not flying anymore. Can you tell us a little bit more about your own personal decisions not to fly, and what impact that can have if more of us make that choice?
Yeah, I just stopped flying because I just couldn't go along with business as usual. It just made me feel terrible to get on an airplane and, you know, think about affecting the planet for hundreds of thousands of years after I'm dead, you know, so I can go have a week at the beach or something. I just couldn't make myself do that anymore. I think that people making personal decisions like that, it's not going to save the world. You know, there's still airplanes in the sky, and I have no illusions about that, but it does seem like, I mean, eventually what has to happen is we have to change our infrastructure so that I can, you know, charge my phone without burning coal, and so I can go see my grandkids without putting CO2 into the atmosphere. And that requires, you know, social changes on a civilizational scale. So, you know, one person saying, I'm not going to eat a hamburger or get on an airplane is not going to save the world, but it makes me feel better. And it does stimulate, I think, if people do that, a larger scale social response, perhaps. I don't know. I just figure if I'm supposed to be the one who is paying attention to the destruction of the world by global warming, at least I'm not going to contribute to it. But that's not the normal atmosphere in academia. We fly to meetings all the time, or we used to back in the old days. We'll have to see what happens going forward. But yeah, let's all go to fly to Iceland or something to talk about global warming. It just seems insane to me. I just wouldn't go along with that.
Right, and I really appreciate and respect that personal choice that you've made. I think the COVID situation and the inability to fly has created a bit of a myth among people that, well, there are fewer planes in the air, so we're emitting less, and so the situation will correct itself. But your analogy of this is like garbage piling up and somebody has to take out the garbage, I think helps to offset the idea that no planes are in the air, so we can't be damaging the earth. Maybe things are getting better. Do you want to speak to that a bit?
Well, it's true that air quality in cities got a lot better with the reduction of traffic and things like that. So, urban smog responds quickly, and if we clean up our act, it cleans itself up. But the rise in atmospheric CO2, I read a paper on this, whether you could detect the pandemic on the atmospheric CO2 rise. And basically, there's such uncertainties in the rest of the fast carbon cycle that you can't. The air quality was a total change that was so obvious you could see it by looking out the window. But the CO2, because it just accumulates, if you slow down the rate of accumulation for a little bit, it doesn't make that much difference. So yeah, that's kind of discouraging in that regard.
And what are your thoughts about like electric vehicles and the impact that they can have? Is that just a new form of transportation that's not really having an impact? Or if enough of us drive electric vehicles, can we really make a change?
Well, any sort of a scheme for avoiding too much global warming includes electrifying everything, including transportation. I have a Tesla, and I feel much better about using it than going to a gas station and filling a car. But whether you can make enough of those for everybody, whether you have enough cobalt and whatever, I can't speak to that. But yeah, electrify everything basically.
Great. And just on the theme of 1.5 degrees, we had a couple questions from the audience members about is 1.5 degrees attainable, and what do you think the safety limit should be if it's not 1.5?
Well, safe would be 350 parts per million. As I said, if you want to consider that there's dangerous stuff happening in the weather now, and we don't want any more of that. The temperature rise is already a degree or more, so we're very close to 1.5. It's if we were bridge engineers, we would never even use the word safe for. This is not a safety limit. This is the best bridge that you guys can afford. It's not safe, but at least if you try to do this one, it's not as bad as if you did that one. So, a bridge engineer would never say this is safe, because that's not what we're talking about. It's more just a target, to try to focus our attention on, I think.
And just to draw, a little bit more detail to that point, when we were talking prior to the event, you mentioned that we're at close to 1.2 or 1.3 already. Is that correct?
I think so. Yeah, it fluctuates. 0.1 degree is pretty small. The global average temperature does fluctuate with El Nino and things like that. So, where exactly we are on on a multi-year average, I'm not totally sure, but we're pretty close.
Do you have a sense of how many years it will take for us to get from 1.2, 1.3 to 1.5? Is that the next 2 years? Is it 10 years? What does that look like?
I would guess sort of decades-ish. I don't really know.
Okay. We did have some other questions that focused a bit on kind of like, what are the human activities that really contribute the most to global warming and the CO2 emission and global warming? People really like to kind of zero in and hone in on their questions on, like, what are the worst polluting activities that we do? Is it air travel? Is it what we eat? Should we all be vegetarians? Is it the fossil fuels we burn in our cars? Like, how would you prioritize that in terms of how people should think?
The average person in the US flies like once a year or something like that. But then you get, academics and business people and rich people, and they're flying 10 times more than that. So the answer would be very different for, one of those people than it would be for kind of the average person. Eating meat is has a big impact on one's carbon footprint. And then there's a lot of energy that we use that we just can't not use. We have to heat our houses and things like that. There does seem to be this sort of low-hanging fruit in travel and eating meat, but ultimately, what we need is a green electrical grid that's not carbon based, and electrifying everything so that we're not allowed to make these sort of planetary destructive decisions.
I noticed in the news that our US President Biden has announced, I believe it's a $2 trillion infrastructure plan. And one of our questions from the audience members is, have you looked at the impact of concrete and cement manufacturing on the climate? And what can we do to sort of re-engineer building materials? Is that a big enough emitter of pollution that is something we should really be thinking about when we're revamping our infrastructure in the United States, especially?
Yeah, concrete, you basically take calcium carbonate and heat it so that the carbon comes out. And so cement manufacture is sort of like 10% of the CO2 emissions. So it's a significant thing, and I don't, really have an answer for how you build big buildings without doing that, but it is definitely an important issue.
We had a couple questions also, and this was one that was on my mind. I jotted it down as you were talking. One is about like the technology that we can use to reduce CO2 and reverse course. And I guess related to that is, would afforestation have some effect on carbon sink in the long term or not? So technology and sort of planting trees. What should we be doing all of the above? And are there technologies that you feel are really promising right now that we should be investing heavily in?
Well, in terms of the biomass first, yeah, having lots of carbon per acre in a forest is better than having very low carbon per acre in some agricultural land or something like that. And so carbon trading schemes oftentimes include credits for allowing forests to grow. The issue with that is whether the trees are going to last forever or not. You might give somebody some cash to let some trees grow in some parkland or something, but then if they cut them down after you give the money, then you've wasted your money. So in carbon trading, you can either sort of pay for forest growth, or you can pay for energy efficiency projects, or you can pay for, there's different categories. And I'm always kind of suspicious about paying for growing trees, because it's, it's not necessarily gonna last. One technology that is being talked about more, there was just a report from the US National Academy of Sciences recommending that we study this more, is geoengineering, putting some kind of haze up in the stratosphere that could cool the planet down. And we know that this would work because volcanic eruptions do this. Mount Pinatubo was the last one. It was a good test for the climate models. It cooled the planet down by 1.5 degrees for a year or two. The difficulty here physically is that it tends to make the planet drier because it decreases evaporation when you change the light field in this way. So you have to look for a delicate balance between, getting the temperature right and not messing up the rainfall too much. And then another more social issue is, how do you decide where, how much of this to do? Technologically, it would be logistically easy enough that some, tiny country could decide to start doing this, and we might not even know about it right away. But then the largest issue with that is just the longevity of the CO2. You put aerosols in the stratosphere and they'll last for a year or two, like Pinatubo, but they won't last for 100,000 years. So you have to keep actively, cooling the planet down in that way. And if somehow things collapsed and they forgot or didn't, do that, then they would get all the global warming all at once. So it's kind of like leaving the planet in a state of life support, for coming generations. It's not a fix, it's more of a Band-Aid, but it's one that people are talking about more and more. There's a really good book on this by Oliver Morton called The Planet Remade that I can recommend if anyone's interested in reading about this startling idea.
We're running out of time, but I have a couple more questions for you. We have a number of people that have logged in from the Philippines, Nepal, Indonesia, and because we have such a diverse audience from around the globe, I'm curious if you have a feel for which countries are going to be most impacted by climate change, that really should be paying attention to this question more than others. And who is leading the way, in your opinion, on addressing CO2 and emissions better than others? We don't have to talk about the bottom players, but maybe are there a couple countries that are really exceeding expectations?
I think in general, the damages are thought to be most impactful in the tropics. The temperate latitudes are where most of the CO2 is coming from unfairly, but the impacts are mostly felt in the warmer parts of the world. I've seen economics papers that show how the temperature of the country affects its economic, or correlates with its economic activity. And Europe and US were kind of optimal, we're at the top of this peak, and getting warmer takes us down the slope a little bit. Maybe the USSR is, a little colder and actually, benefits, not the USSR, Russia. Not a social scientist guy, right? Obviously. And then the tropics, are already kind of on the down slope of this curve, and getting warmer is a real hit for them, a bad thing. In terms of who's pushing forward, the Scandinavian countries and New Zealand, they seem to be more proactive about, like in Norway, they've gone much more toward electric vehicles, for example, than we have. Maybe the smaller countries are better able to adjust these issues. I don't know.
So Professor Archer, thank you so much. We really appreciate all your thoughts on the program tonight. I did want to give a plug for your MOOC, and we have so many people that are interested in learning more. I just thought that would be a great place to direct them. So could you tell people how they can access your MOOC programs on Coursera, and tell us a little bit more about that before we leave you?
Sure. It's on Coursera.org, and it used to be free. My last I heard, there was a way you could pay a little bit of money and it would authenticate you so that you could use it as somewhat more of a credential, but it consists of a bunch of little 5-minute lectures, and I have climate models of various types that run interactively on the web, so you can change the CO2 setting and see how it changes the the infrared light in the atmosphere, or you can look at different climate model results and see how rainfall is changing in some forecast or other. And there are exercises in the MOOC that have you use those models. So it's all based on a class that I did for non-science undergrads as part of the University of Chicago's core curriculum, where non-scientists had to take a few science classes and vice versa. So I had many years of talking to English majors and philosophy majors and econ majors and other sorts of non-science types like that. It kind of smooth, over the years, I hope it sort of smoothed out the rough edges, and then Coursera was an opportunity to kind of port that into a massive open online class.
Well, one thing we can do is we're going to develop this 1.5 degrees resource page on our website. So we'll get the link for your MOOC and we'll put it on the resource page so that people can access it there. And thank you so much for being the person that launched our 1.5 degree program and for advising me and our team on how we should move forward with this program. I really appreciate it, and we'll definitely be in touch with you as we move forward over the next year or so to try to address more issues around climate. So thanks so much for joining us tonight. We really appreciate it.
Thank you, Mark. It's been an honor.
And for everyone else who's joined us in Hong Kong and around the world and throughout Asia, please stay tuned for our next 1.5 degree program. And remember, you can find us at www.uchicago.hk. Have a great evening.